Some sums can be summarized with simple formulas. My favorite examples are the triangular numbers, 1 plus 2 plus 3 up to x, and geometric sums, r to the 1 plus r to the 2 up to r to the x. In high school, I was amazed to learn that the first sum is equal to x times x plus 1 over 2, and the second sum is equal to this expression. But what caught my attention about these wasn't just their simplicity or their clever derivations. Rather, it was the fact that they extend the domain of the sum. See, summation is a fundamentally discrete operation. The original expressions don't make any sense unless x is a whole number. But with these new formulas on the right, you can plug in 1/2, pi, or even I, and you'll get an answer. So I wondered, is there a way to extend the domain of any sum? I spent a lot of time thinking about this, which ended up being worthwhile, because it gave me enough math for 2 whole videos. Hang on, 3 whole videos. In my first video, I solved this problem for the function 1 over x, and in my second video, though this wasn't the primary topic, I solved it for the natural logarithm of x. But these are just 2 out of the infinitely many functions that exist. There has to be some general method to extend the sum of any function. Well, for a pretty broad class of functions, there is. That's what I'll derive in this video. After I began working on this video, I discovered that this topic has already been explored and published in a handful of journals. Though the bulk of this video will be spent on my derivation, I'll go over the published approach afterwards, and we'll see that the 2 solutions are largely the same. I've tried to make this video self-contained, and I'll be repeating some of the ideas from my other videos, so they aren't prerequisites. But if it feels like I'm going too fast, feel free to watch them. I won't mind. I will be making heavy use of summation notation, so you'll understand this video best if you have a solid grasp of it. It'll also help if you're familiar with limits, but apart from that, no calculus is required. Now, if you do know calculus, your mind may have jumped straight to integrals when you heard the problem. Integrals are approximated by sums, and you'd be right to note that, in a certain sense, integration is the continuous version of summation. But not in the sense I'm after. Even though these concepts play analogous roles in the continuous and discrete worlds, it's not always easy to jump between these worlds. So we won't see any integrals. Instead, we'll discover some more discrete analogs of concepts from calculus. But don't worry about this. This isn't really a video about discrete calculus, and I'm getting ahead of myself. Let's go back and take a closer look at the problem. Given some function f of x, it could be anything, we'll be trying to extend the sum of f of k, where k goes from 1 to x. This itself is a function of x, and to help us think about it that way, I'll represent it with s of x, s for sum. Now, since this sum only makes sense when x is a whole number, the plot of s of x is a discrete set of points. So when I ask how to extend s of x to take in any number, I'm essentially asking how we can connect all these points in a natural way. Well, there clearly is no single solution. We could just draw straight lines between the dots, or we could find some smoother way using any number of methods. You could probably make a case for any function that touches all the points. So how can we find the solution that's objectively the best? Well, we can't, because best is a subjective term. But what we can do is play around with s of x and find certain properties that it has, or equations that it satisfies, which do make sense for any number x. Then, by decreeing that these properties must hold for any x, we'll be able to constrain the solution space down to one answer. So, to get started, I'll revisit the 2 main observations from my other videos. The first observation is that s of x follows a simple recursive formula. Let's look at s of x plus 1. This is f of 1 plus f of 2 plus f of 3, and so on up to f of x, and finally f of x plus 1. But everything except for this last term is just the definition of s of x. So we can substitute that in, and we're left with this. S of x plus 1 is s of x plus f of x plus 1. So with nothing other than the starting point that s of 1 equals f of 1, we can use this formula to determine all the points of s. To get s of 2, we just add f of 2. Then to get s of 3, add f of 3 to that. And we can continue this as far as we want. But there's a bit more here. We can also use this in reverse. If I replace x with x minus 1 and move things around a bit, we get a formula that tells us how to get s of x minus 1. Just subtract f of x from s of x. So we can step backwards as well. And we can even go backwards past our starting point, computing s of 0, which will always be 0, and s of negative 1, and so on forever. But what really makes this recursive formula useful is that it's not restricted to integers at all. If we could somehow define s for some non-integer number, for example if we found that there was a point here, then we could use this formula to find the next point and the previous point, and by repeating it, we could find an infinite sequence of points in both directions. This, particularly in the negative direction, will play a key role in our process. The other key insight from my previous videos was that, although we don't know how to extend s of x near the origin, we can extend it when we look really far to the right. In my first video, f of x was 1 over x. This function has one property which turns out to be useful. It approaches 0 as x approaches infinity. So when we go really far to the right, taking s of some huge number, which I'm just calling n, the amount that we add to get the next point, f of n plus 1, is pretty much 0. And the same goes for all the following steps. So since we're adding pretty much 0 each time, the points all flatten out. In other words, s behaves like a horizontal line, or a constant over here. So it's natural to extend it with a horizontal line. In my second video, f of x was the natural logarithm of x. This one was trickier because the function doesn't approach 0. But it does flatten out more and more as you look further to the right, appearing increasingly like a horizontal line, or a constant. So again, letting n represent a huge number, the amounts that we add to get the next points, f of n plus 1, f of n plus 2, f of n plus 3, and so on, will be pretty much the same. And adding the same amount at each step is the recipe for making a sloped line. Therefore, it's natural to say that a sloped line is the correct way to extend s over here. So, we've seen that s of x follows a recursive formula, and that, at least for two specific examples, we were able to extend it for large inputs. But how does this help us extend it everywhere? Well, let's see. Suppose that the s function can be extended in the vicinity of some huge number n. Okay, here n is only 21, which isn't huge, but that's just because I have to fit it on the screen. Now, if we want to find s of x for some non-integer x, we can get there by a 3-step process. Step 1 is to forget about x and to fly past it, going straight to s of n. This puts us in the zone where we do have an extension, so now we can jump forward any amount. Step 2 is then to jump forward x units, giving us s of n plus x. Finally, step 3 is to use the recursive formula to step backwards n times. This puts us back to x with a specific value locked in for s of x. And no matter what x we choose, this process will let us compute s of x. Now, there's one wrench in this plan. We have to actually be able to extend s near n. But apart from the two examples I showed, that's a fantasy. So for now, x will still have to be an integer, but that's a problem for later. Right now, let's turn this process into a formula. Step 1 is easy. S of n is defined as this sum. So on to step 2. To move from s of n to s of n plus x, we use the recursive formula x times, adding f of n plus 1, then f of n plus 2, and so on up to f of n plus x. This is the sum of f of n plus k, with k going from 1 to x. Finally, for step 3, we use the recursive formula backward n times. So we subtract f of x plus n, and we keep subtracting, making our way down to f of x plus 2, and finally f of x plus 1. We can condense this step into a summation as well. We're subtracting the sum of f of x plus k, with k ranging from 1 to n. So these are the mathematical expressions for our 3 steps, and combining them together gives us a new formula for s of x. Now, I'm going to make a couple modifications. First, I'll swap the last 2 sums. My reason for doing this is that these 2 sums both have the same bounds. They go from 1 to n, so we can combine them into a single sum. Now, this formula is perfectly valid no matter what the value of n is, as long as it's a whole number. I said that n would be a really big number, but how big does it need to be exactly? The answer is arbitrarily big. We'll take the limit as n goes to infinity. Now, what you see here is our key formula. This certainly is more complicated than our original definition of s of x, but there's nothing magical about it, yet. It still only makes sense if x is a whole number. Well, this first sum actually does work for any value of x because its upper bound is n. It doesn't care what x is. But the upper bound of the second sum is x, so we still need x to be a whole number. But now, this problematic sum is offset by n, and by taking the limit as n goes to infinity, we're deferring the problem arbitrarily far to the right, where f of x, hopefully, behaves better. Now we're just one step away from our first result. If you recall, I mentioned that in a previous video, I solved the problem for a function that approached 0. We can easily repeat that solution now. So let's say that f of x is some function that approaches 0 as x approaches infinity. Well, since we're taking the limit as n approaches infinity, this f of n plus k approaches 0. And the sum that it's inside of goes from 1 to x. Well, no matter what x is, it'll be finite, so we're adding finitely many things that all approach 0. This means that the whole sum approaches 0. Thus, it vanishes when we take the limit, so we can drop it. With that, we've just removed the only part of the formula that required x to be an integer, so we're done. Let's see this in action. I'm in the Desmos graphing calculator, and I'm letting f of x be x to the power of p, constrained to take only positive inputs. I can choose any value between -3 and +3 for p, and as long as it's negative, f of x will approach 0. Now, this expression here looks a bit complicated, but it just plots the integer points of the sum. Finally, I have the solution we just found. Well, my computer can't really do a limit, so I'm just setting n to be 100. And when I make it visible, sweet! It smoothly passes through all the points. Now, if I increase p too much, you can see it starts to falter a bit. This is because the larger p is, the slower x to the p approaches 0, and we need to crank up the value of n to compensate. But if I keep increasing p, and I go to a positive number, it just breaks completely. This is because our f of x no longer approaches 0, so we've lost the key ingredient for this solution. So let's fix this. So, we've solved the problem for functions that approach 0 as x approaches infinity. Following the progression from my other videos, up next will be functions that flatten out when x approaches infinity. But the phrase, "it flattens out," isn't exactly something we can put in an equation. So what does this really mean mathematically? Well, using the logarithm as our function, I'll start with a reasonable but incorrect answer. We might think that for a function to flatten out, it must approach a constant. But this would be too restrictive. Despite the logarithm flattening out in a useful way, it actually grows past any constant we could come up with. It diverges to infinity. So we need some looser definition. Fortunately, we've kind of already seen such a definition in this video. Remember when I was reviewing my first video, how I said that because f of x approached 0, the points of s of x flattened out? Well, we can use this as our definition. We can say that s of x flattens out if f of x approaches 0. Okay, I admit it doesn't make too much sense to define a property of one function, s, in terms of another function, f. If we didn't know that these two functions were related to each other, this definition would be nonsense. But we can fix this with our handy-dandy recursive formula. If we rearrange it a bit, we see that s of x plus 1 minus s of x is equal to f of x plus 1. So if one side of this expression approaches 0, then so does the other side. And of course, this plus 1 doesn't really matter when x is going to infinity, so we can drop it. So f of x approaches 0 precisely when s of x plus 1 minus s of x approaches 0. So we can use that as our definition of what it means for s to flatten out. And of course, the name of the function doesn't matter, so we can use this for any function. Now, this expression, f of x plus 1 minus f of x, is something that has its own name and notation. It's called the forward difference of f, evaluated at x, and we can write it as delta f of x. This lets us save a bit of space, as we can just say that we're looking for functions where delta f of x approaches 0. You might be wondering why something this simple deserves its own name and notation. Well, in the same sense that a sum is the discrete version of an integral, the forward difference is a discrete version of the derivative. In fact, let's take a look at the rearranged recursive formula again, and let's express it using the forward difference. Remember, s was defined as the sum of f, and now this tells us that taking the forward difference of s brings us back to f. So the forward difference and summation are inverses of each other. This is essentially a discrete version of the fundamental theorem of calculus. Oh, sorry, I said that I wouldn't bring calculus into this. This isn't really important, but I just couldn't let it slip by without mentioning it. Let's get back on track. What's important is that the forward difference, delta f of x, is defined as this. Now, another way to think about the forward difference is that it's the amount you add every time you step one unit to the right. We can move the f of x to the other side, and actually it's cleaner if we swap both sides completely. Now we see that f of x plus 1 is f of x plus delta f of x. This is a recursive formula, just like we had for s. So let's say we have some starting point, f of a, and we want to compute f of a plus b, where b is a whole number. By using this formula, we can get there by stepping forward b times. For the first step, we add delta f of a, then we add delta f of a plus 1, and then delta f of a plus 2, and so on, up to delta f of a plus b minus 1. Now, this whole process can be represented in summation notation. Here we're adding up delta f of a plus k, where k ranges from 0 to b minus 1. So let's substitute that in. And finally, I'll swap the sides of the equation. The resulting identity expresses f of a plus b as f of a plus a sum of forward differences. This will play a key role in our solution. And actually, it's a discrete version of a variation of the fundamental theorem of calculus, but don't worry about that. Anyway, we're now ready for our second solution. Let's say we have some function whose forward difference approaches 0. Let me bring back the main formula for s of x. Remember, this sum is the only thing preventing us from plugging in any value of x. And last time, the key was that this term approached 0, which allowed us to drop the whole sum. But this time, delta f of x approaches 0, which doesn't immediately help us. But that's where this forward difference formula comes into play. Well, first things first, both these equations introduce the letter k, so I'll rename them to k1 in the first equation and k2 in the second to avoid a conflict. Now we can let a be n, and we can let b be k1, giving us the desired f of n plus k1. Now, in the formula for s of x, this term is in a sum, so we'll take that sum of both sides to make it match. Finally, on the right side, we can distribute the outer sum to both terms. Now we can substitute this whole thing back in. Here's what we've accomplished. We've turned the problematic sum into a double sum of delta f. And since delta f approaches 0 as its argument increases, this delta f of n plus k2 will approach 0 when n goes to infinity. The double sum may look scary, but regardless of what x is, it will only be summing finitely many terms. And if finitely many terms all approach 0, then so does their sum. So just like last time, we can drop this whole thing. Now, there's still this sum left over, but it's a lot simpler. We're just summing f of n x times. This is the same thing as x times f of n, and when we express it like that, it doesn't matter what x is. So with that, we have our solution for functions whose forward differences approach 0. Let's see it in action. So I'm back in the Desmos graph where we left off, and the previous solution is completely shooting down in the wrong direction. Now, the new solution is the same thing, but with x f of n added to the end. And we can see that fixes it. Also, for functions that already converged, this new solution converges way faster. For instance, with this value of p, n would have had to be in the millions for it to look this good with the old solution. But now it looks perfect with just 500. Now, just like last time, it really starts to struggle when I make p bigger. And if p surpasses 1, it breaks completely. This is because f of x no longer flattens out. So let's see how to extend this further. Let's look back at what we've done so far. First, we extended the sums of functions that approach 0. Then we extended the sums of a broader class of functions, functions whose forward differences approach 0. So if taking the forward difference expanded the set of functions we could work with, how can we expand it further? Take the forward difference again. That's right, we'll be iterating forward differences. This double forward difference is defined exactly as you'd expect. That is, it's the definition of the forward difference applied to the forward difference. Now, instead of writing delta delta f, we can just write delta squared f. This is called the second order forward difference. We can also take the forward difference of this to get the third order forward difference, delta cubed, and we can keep going as far as we want. Now, to make the notation consistent, we can say that the ordinary forward difference is delta to the 1. And actually, it makes sense to define the 0th order forward difference of f as just f, because we've applied the forward difference 0 times. So, now that we've defined all these forward differences, we can see exactly where we're headed. We've extended the sums of the functions whose 0th or first forward differences approach 0, and going forward, we'll do the same for all these subsequent cases. But don't worry, we don't have to tackle each of these one by one. That would be a very long video. The tools we've developed in the first two solutions are enough to solve all these others at once. Now, a quick note for anyone who's familiar with asymptotic notation. The 0th order functions are the functions in little o of x to the 0. Also, if a function's first order forward difference approaches 0, then it's in little o of x to the 1. And in general, if the nth forward difference approaches 0, then the function is in little o of x to the n. So by the end of the video, we'll be able to tackle any polynomial growth rate. Anyway, let's move on. Our key tool will be this forward difference formula we found earlier. Only now, I'll explicitly mark the orders of the forward differences. So this formula turns the 0th order forward difference into a sum of first order forward differences. In other words, it increases the order by 1. Now, we could just as easily apply this formula to the first order forward difference of f, to express it as a sum of the second order forward difference. Or we could have applied it to delta squared, or delta cubed, or generally, delta to the n, turning it into a sum of delta to the n plus 1. This will be important, because by iterating this formula, we can increase the order of the forward differences as much as we want. Let's get on to the solution and see how this works. Here's our main formula for s. The first step will be to make a couple superficial changes. First, I'll replace n with n minus 1, which doesn't change anything since we're taking the limit as n goes to infinity. Now, if we look at this sum, we're summing f of n plus k minus 1, with k going from 1 to x. But since we have k minus 1, this is the same thing as summing f of n plus k, where k ranges from 0 to x minus 1. And finally, I'll explicitly mark this as the 0th forward difference of f, and I'll rename k to k1, because I remember we had to rename it last time. These changes may seem random, but trust me, since I've seen the solution, I know in hindsight that they'll make things cleaner. Now, for this derivation, I'll focus on the specific case where the third order forward difference approaches 0. This should feel general enough that it'll be clear how to extend the solution to every case. We'll basically do the same thing we did last time. We'll focus on the term in this last sum, and we'll bring in our forward difference formula. I've already named the index of this new sum k2. We can let a represent n and let b represent k1 so that the left side matches the term we're after. But since it's in a sum in the upper formula, we'll take that sum of both sides. Then we can distribute the outer sum in the right side, and we can substitute this new expression in. Last time, this was all we had to do. But this time, the first order forward difference doesn't necessarily approach 0, so we can't drop anything. So, we repeat the same exact process for the delta to the 1 f of n plus k2. Here's the forward difference formula, only this time it's acting on the first forward difference rather than the 0th. Note that since we already have k1 and k2, I'm calling the index here k3. Like before, we'll let a be n and we'll let b be k2, so that the left side matches the highlighted term above. But this term is inside a double sum, so we'll take that double sum of both sides of our equation. And then we'll distribute this double sum in the right-hand side. This whole thing was just a repeat of the process we already did. Let's go ahead and substitute the result back in. Now, this still isn't enough because we've only raised the forward difference to the second order. We need the third order. But we can repeat this process as many times as we want, so let's do it once more. Here's the forward difference formula again, this time acting on delta squared f of n plus k3. Since we've seen the process twice, I've skipped past the basic substitutions. Now, this time, we have a triple sum in the top formula, so we need to take the triple sum of both sides. And then, in the right side, we can distribute the triple sum. Now, let's substitute this in. And now, finally, we've increased the order of the forward difference enough. Since delta cubed f of x approaches 0, this term will approach 0 as n goes to infinity. Even though it's in a sum of a sum of a sum of a sum, the number of terms we sum is ultimately determined by the value of x. And for any whole number x, we'll only sum finitely many terms. And as before, a finite sum of terms which all approach 0 will itself approach 0, so we can drop it completely. And now, at last, we've gotten rid of the problematic part of this expression, so we finally have our formula for s of x. All we have left to do is, well, take all these nested sums and, I might have gotten a bit ahead of myself. So it appears that I've made things worse. We started with just one sum, and now we have a series of 3 increasingly nested sums. And these nested sums are tangled together because the upper bound of each inner sum depends on the index of the previous one. And at the end, they all depend on x, so we need x to be a whole number. Sure, we saw that this single sum is easy to simplify, but the double sum is trickier, and the triple sum wouldn't be fun. And we only had to do 3 iterations. What if the 10th order forward difference approached 0? Then we would have had to repeat the process 10 times, and the resulting nightmare of an expression would have ended with 10 nested sums, which I don't even want to think about. Ugh, let's not. 3 iterations is plenty. Well, despite what I just said, there is one nice thing about these nested sums. They don't have anything to do with the specific function f. We used to have f of n plus k in the sum, but now there's no mention of k here, just n. But n doesn't depend on the sums, so as far as the sums are concerned, these terms are all just constant. Therefore, we can factor them out and consider the sums to be of 1. Now, some of you might recognize these nested sums, but if you don't, you could waste quite a bit of time trying to simplify them. Trust me, I know. But if we look at these just right, we'll find that they're actually equal to something simple and familiar. We're in the final stretch now, so buckle up. I'll just look at the triple sum, because the answer will easily generalize to any level of nesting. Let's start by looking at the lower bounds of all these sums. They all start at 0, but we can optimize this a bit. Let's think about what happens to the last sum when k2 is 0. The upper bound, k2 minus 1, will be negative 1. But the lower bound, 0, is already greater than negative 1. So this sum is over before it even starts, and nothing happens. Therefore, we can skip the step when k2 is 0, and just start it at 1. Similarly, we can look at the middle sum when k1 is 0 or 1. The upper bounds of this sum would then be negative 1 or 0, which are both less than the lower bound of 1. So in both cases, the sum would be over before it started. This means that we can skip 0 and 1 and just start k1 at 2. And if we had more sums, this pattern would continue. The lower bounds would keep increasing by 1 as we go to the left. Alright, admittedly this doesn't help much yet, but now let's visualize what this triple sum is doing. To make a concrete example, let's say that x equals 10. I'll list 10 points labeled 0 through 9, which we'll use to track the values of k1, k2, and k3. So, focusing only on the first sum, k1 starts at 2, and at each step it increases by 1. Simple enough. Now, for each value of k1, k2 starts at 1, and it repeatedly increases by 1. Since its upper bound is k1 minus 1, its last step is directly to the left of k1. After that, k1 increments, and the second sum starts over, so k2 resets to 1 and starts going again. Now for each value of k2, k3 starts at 0, and it increases by 1 at each step, going up until it's directly to the left of k2. Then the third sum is finished, so k2 increments, and k3 starts over at 0. Finally, for each step we're adding 1, so I'll keep track of the running total, and each time k3 moves, we add 1 to it. We keep following this procedure until all the points are as far to the right as possible. So we can see that, when x equals 10, the value of this triple sum is 120. Let's rewind back to the beginning and watch the whole process from start to finish. Pay attention to the way the 3 points move. Can you see what's happening here? The 3 summation indexes are systematically stepping through every possible choice of 3 out of 10 points. Here, let me illustrate. I'll choose 3 points at random, let's say these ones. As we run through the sum, k1 will eventually arrive at the rightmost point I chose. Then, before it can move again, k2 will make its way to my middle choice. And before it can move, k3 will arrive at my leftmost choice. And this particular choice is only counted once, because for every subsequent step, at least one index will be to the right of its target item. So no matter which 3 points I choose, the state will coincide with my choice exactly once, which will contribute exactly 1 to the running total. This means that this triply nested nightmare sum is just a way of counting how many ways there are to pick 3 out of X items. Isn't that just like the coolest thing ever? Anyway, the number of ways of picking a certain number of items is called a binomial coefficient, or a combination. There are varying notations for it, which mostly involve slapping the parameters on random corners of a capital C. But I'll use this one because it just looks so nice. We read this as x choose 3. Now, I used the triple sum as an example, but the same thing would have happened for any level of nesting. So the result of m nested sums would be x choose m. Now, this still feels like a pretty discrete process. On the surface, it doesn't make sense to count the number of ways of choosing 3 of x items when x isn't a whole number. But mathematically, it works out. If we have x items, and we want to choose 3, we start by choosing 1 out of the x items, so we have x total choices. Then, whichever item we chose, there are x minus 1 remaining items from which we can choose our second item. And now that we've chosen 2, there are x minus 2 options for the third item. So we have x times x minus 1 times x minus 2 ways of choosing. But we've overcounted, since we counted each possible order that we could have chosen these 3 items in. Since there are 3 factorial ways to order 3 things, we just have to divide by 3 factorial to get the true answer. And this answer does not require x to be an integer. In general, this is the formula for x choose m. So now we can finally finish our solution. Remember, this was our formula for s of x when the third forward difference of f approached 0. But now we know that all these nested sums are just binomial coefficients, so here's our true solution. Now, I know you feel like you just haven't seen enough summations in this video, so I'll add one more. These 3 terms at the end all follow the same pattern, so we can represent them with a summation as well. And I guess for personal preference, I'll swap the order of the binomial coefficient and the forward difference. Now, this is the solution for when the third forward difference approaches 0, but if the mth forward difference approached 0, we would just have m terms in our sum, giving us the fully general solution. Alright, let's go back to our graph to see this work. Now, Desmos doesn't have forward differences built in, so I've manually entered the first few as D0, D1, D2, and D3. Desmos does support binomial coefficients through the built-in NCR function. I've added 4 terms here, so we can handle growth rates up to x to the 4th. So this works for all the values of p that I can choose with this slider. Mission accomplished. One quick note. At the beginning, I said that we would be decreeing that certain formulas hold for every number x. I should be explicit about what these were. They were the recursive formula, the equality of nested sums and binomial coefficients, and wherever we used the fact that something approached 0. These are all unambiguously true when x is a whole number, but they can neither be proven nor disproven otherwise. But by decreeing that they do hold everywhere, we were able to derive a formula that lets us sum any function up to a fractional or even irrational number of terms. Actually, this works perfectly well even for complex numbers too. But that sounds like something for another video. Well, I suppose it's not quite true to say that we can do this for any function. The function must have some forward difference which approaches 0, so it has to have a polynomial growth rate. And there's another hidden but obvious condition. The limit has to actually converge. This can fail if f of x isn't nice enough, but it's tough to find a precise condition other than that the limit must exist. But this does work for all rational functions, logarithms, non-integer powers, and most combinations of these. Let's see a few. Alright, when I first started this video, I thought that this was the end of the story. But a viewer sent me some links to some resources that were broadly related to my other videos, probably unaware that they were guiding me to a published solution. It turns out that I wasn't the only high school student to get hooked on this problem. A couple of decades earlier, a teenager named Marcus Mueller went on a similar journey. He found an equivalent solution, invented a stylish notation for it, and used his solution to come up with a bunch of crazy identities. I'll summarize his method here, but if you want the full details, you can find his papers linked in the description. Mueller had the same idea about going really far to the right and extending the sum over there, so his solution essentially uses the same key formula that we used in this video. But you won't find any forward differences or binomial coefficients in his work. Instead, he found a more fundamental way of extending the sum. It all comes down to polynomials. See, it turns out that the sum of any polynomial is itself a polynomial, whose degree is 1 higher than the original degree. Now, how to find this new polynomial is its own topic, but we don't need to go there. We just need to know that it's possible. So this fact led Mueller to realize that if f of x behaves like a polynomial for large inputs, then s of x will behave like a polynomial of 1 higher degree. And since you can plug any real or complex number into a polynomial, this can help us plug any number into S. Of course, we have some details to work out here. What exactly do I mean when I say that f of x behaves like a polynomial? Well, let's start simple with degree 0 polynomials, also known as, well, constants. Remember, earlier I put forward the idea that perhaps we could say that a function behaves like a constant if it approaches a constant. But I threw this idea out because it was too restrictive. Some functions that we'd like to say behave like constants, such as the logarithm, don't approach any constant. But maybe I was too hasty to abandon this idea. The logarithm really is well approximated by constants. We just need different constants to approximate it in different places. Okay, that might seem like cheating. If we move the constant around, then it's not really constant, is it? But we can still use this. If we fly out really far to the right, and we move the constant along with us, it becomes a better and better approximation over an increasingly wide interval. This is the sense in which the function behaves like a constant. Let's make this idea precise. For every whole number n, let's find a constant that approximates the function near n, and let's call it c sub n. So we'll have an infinite sequence of constants, c1, c2, c3, and so on. But how can we formalize the condition that the approximations get better as we move to the right? Well, we can look at any point relative to n. That is, n plus a half, n minus pi, n plus 5, you name it. For each of these points, let's look at the difference between the function and the constant. As we step forward, choosing larger and larger n, these distances all approach 0. In fact, for every number x, the difference f of n plus x minus c sub n approaches 0 as n approaches infinity. This gives us the definition. A function behaves like a constant if there exists a sequence of constants, c1, c2, c3, and so on, such that for every x, this limit equals 0. Now, this definition is about constants, but remember, constants are just degree 0 polynomials. So I'll replace the sequence c sub n with p sub n to signify that they're polynomials. But there's really nothing special about the degree of the polynomials being 0. If instead we had degree m polynomials for any m, this would still be a reasonable definition. So how does this help us? Well, let's say that f of x does behave like a polynomial of some degree. That is, you can find a sequence of polynomials for which this limit holds. Well, let's look at our main formula for s of x. Remember, this last sum of f of n plus k is what we need to extend. But since f behaves like a polynomial, the difference between f of n plus k and p sub n of n plus k approaches 0 as n approaches infinity. This means that we can substitute p sub n in place of f without changing the limit. So now we have the sum of the polynomial p sub n. But remember, the sum of a polynomial is itself a polynomial. So this whole sum is a polynomial. I'll represent it with capital P sub n. Now, since this is a polynomial, we can plug any number into it. So we're done. We have our fully general solution. This approach really gets to the heart of what's going on without worrying about the implementation details. What I mean by this is that it captures the big idea, going off to the right and approximating the function arbitrarily well with polynomials, but it doesn't prescribe any specific method for finding the sequence of polynomials. We could use Taylor polynomials or maybe some other method, but we'd get the same result no matter what we used, so the specific sequence isn't relevant. Wait a second. If this is all about polynomials, what was all that crazy stuff we did with forward differences? Is our solution from earlier completely different? No, it's actually a specific instance of Euler's solution. See, these two formulas are identical, except the top one has p sub n of x, while the bottom one has the sum of binomial coefficients and forward differences. But this sum is a polynomial of degree m. This means that the bottom expression is an example of the top expression, where the polynomial p sub n happens to be given by this sum. But what exactly is this polynomial, and is it really a valid possibility with Euler's method? Let's see. Remember, in Euler's solution, big P sub n is defined as the unique polynomial that equals this sum of little p sub n for all the whole numbers. But its real significance is that, as n goes to infinity, it becomes arbitrarily close to the same sum, but of f. This is what allowed us to use it in the final formula. Now, it'd be pretty easy to symbolically prove that our polynomial has this property, but I think we'll get a clearer picture by graphing it. Let's consider the case when m equals 3, so our p sub n will be a degree 3 polynomial. Let's say that the sum of f of n plus k looks like this. And let's see how our polynomial does. See what's happening? Our polynomial perfectly passes through the points of the sum at 0, 1, 2, and 3. In fact, this is the only degree 3 polynomial that passes through these 4 points. That's about as good an approximation as we could ever hope for. If any degree 3 polynomial fits the bill, this one does. In fact, for any m, our formula gives us the unique degree m polynomial that equals the sum for all the points from 0 to m. This is actually a 350-year-old method of polynomial interpolation called the Gregory-Newton Formula. Well, this looks a bit different than what you'll usually see because we're applying the Gregory-Newton Formula to this sum. Normally, it would just be applied to the function, which would look like this. Now, there's one final connection here I want to share. If you squint your eyes, this formula might look a bit familiar. That's because Gregory-Newton polynomials are the discrete version of Taylor polynomials. And that's where I'll end things. There is a lot more to be said about discrete calculus, but there are some other great videos on the topic, and if I wander any further in that direction, this video will never end. We've accomplished our goal, and we now have an explicit formula for extending sums of a broad range of functions. I hope the process was as interesting to you as it was for me. Thanks for watching.